What's cracking, guys? In this video I'm covering end-to-end object detection with transformers, or DETR for short, by Nicholas Carrion, Francisco Massa and others from Facebook AI Research. So obviously it's about object detection and they are using transformers. So they mentioned here that the main ingredients of the new framework called DETR are set-based global laws that forces unique predictions via bipartite matching. It's a mouthful, we'll break that down in a minute. And a transformer encoder-decoder architecture. So the basic premise here is they are training this detection pipeline using end-to-end learning, and they're using as the differentiable blob, they're using transformers. So those are the two main ideas. And comparing that to previous object detection pipelines, like if you're familiar with that, basically most of them consist out of multiple stages. So as you can see here on the left side, basically we have, so the stage one just outputs a bunch of these different region proposals. So all of these boxes are kind of claiming that they see a car inside of that box, and the idea is to just kind of filter out and leave just the best one. And in this case, this non-max suppression algorithm works perfectly. So basically, after stage one proposes these regions, we have this heuristic called non-max suppression algorithm, and it just basically filters out the best box. And the way it works is super simple. Basically, you find the box with the highest confidence that this is a car, and then what you do, you just set some threshold, and you find the IOU, or the intersection over union, with other boxes, and you just kind of filter out those boxes that have whose IOU crosses that threshold. Okay, so I just went ahead and pasted this IOU definition so that I can better explain how this NMS algorithm, so non-max suppression, works. So as I said, we have two stages usually. The first stage proposes a bunch of these different regions, and all of those boxes kind of claim that they see a car inside of it. But we want to just leave a single one that has the highest confidence and the best bounding box. And the way we do that is the following. So out of all of these boxes, we'll just find the one with the highest confidence score. And then we're just gonna set a threshold, for example, I don't know, like 0.7, and we're going to remove all of those boxes whose IOU is bigger than 0.7. That means, in human language, those boxes that overlap too much with the box with the highest confidence, those will be removed. And IOU is just defined like this. So you find the intersection between the two boxes, you find the union, and you just divide the two. As you can see, as the overlap becomes bigger, this IOU will tend to 1. And as the overlap becomes smaller, this IOU will drop to 0. Okay, that's the basic idea. So we wanna, the whole idea of the DETR pipeline is to remove this heuristic and kind of train this whole system detection pipeline end to end without these multiple stages, without these heuristics such as the NMS. And this is not the only method out there, but that's the one that I took as an example. And yeah, that's it. So with the motivation out of the way, let's see how DETR works. So jumping to this high-level explanation of the pipeline, we have how the thing flows is we have an image at the input, we pass it through a CNN, which will downsample the spatial extent and increase the number of channels, so we'll end up with multiple feature maps here, so something like HW times C, where C is the number of channels, and initially we maybe have something like H0, we have W0, and we have 3 in the case of RGB images. So after we have these feature maps, what we do is we're gonna flatten them out and pass them as tokens into the transformer. And later we'll just unpack how this works in the next diagram, but here just stick with me. So basically we just kind of process all of these tokens similarly to the vision transformer. You can treat it that way. And what happens is at the output of the decoder, we have a bunch of these different region proposals. So we'll have a fixed number of these, and we're using 100. So we'll have 100 proposals, and each of these boxes has 2 pieces of information. So we can treat this box, it will just be a 2 tuple. So we'll have 2 tuples. So we'll have one tuple will tell us about the actual box. So what's the center coordinate and what's the height and width of the box. So that will be 4 numbers. So we'll have like CX, that's the center coordinate on the x-axis, then we have the center coordinate on the y-axis, we have the height of the box, and we have the width of the box. So in the case of this red one, So obviously this would be the center, then we had the height, and we had the width. So that's the output. Now the second piece of information that's vital is which kind of object is that, and that's where the second tuple comes in, and this tuple will just contain C number of classes plus 1, where this is just the cardinal number of the classes set. So that means, for example, if we have, I don't know, 10 classes like dog, cat, whatever, we'll have 10 here, and plus 1 is because of this no object class. So sometimes a box like this green one is just a spurious box, and it doesn't contain any object, so that's why we include plus 1. So that will be the output, and all of these 100 outputs will contain exactly these two tuples. So that's the output information. Now the interesting part is, how do we actually match these so that we can compare them, and how do we backprop these through the encoder and the CNN and train the DETR pipeline? So the idea is fairly simple. The first thing we do is this bipartite matching, and I'll explain that in a bit more detail, but the rough idea is to find the permutation. So basically, if we focus on the ground truth, the ground truth here will be something like this. So we'll have, let me just draw it like this. So we'll have a bunch of outputs, and the first one will be this, let's say this red box is the first output in the ground truth, and then the second output will be this, maybe this yellow one. I'll just denote it like this. So we'll have, so this will be the two outputs, and then we have a bunch of these no object like proposals. And so as you can see, the goal will be to kind of learn how to find a permutation, how to associate this one to this one, and how to associate this box with this box. So we'll basically want to find a way how to sort this so that we have this red box standing in the first place, and then the yellow box being in the second place, and all of the other no object proposals should be here. And once we have that, then we can just kind of compare them because they're matched, right? Because if we didn't do that, it just wouldn't make any sense. So again, on a high level, we first do the sorting using this Hungarian matching algorithm. And the second thing is we just compare them. So obviously you can think of it, we'll basically want to compare the boxes. So the red box here and the red box here will somehow include the IOU in the loss, will somehow include all of those 4 coordinates in the loss, as well as the class information. So for example, this here, so the red class for this proposal will be equal to 1, so the probability is 100%. Here maybe our prediction is not that good, so it's predicting maybe 0.7 for this red class, and we want to push that 0.7 towards 1. Okay, that was it in a nutshell. Now let me start digging into more details so that this becomes way more clear than it currently is. Okay. Let's find and I'll explain all of these equations in a second. I just want to focus first on the expanded diagram of that same pipeline. So again, we have CNN, we have these feature maps, and we'll have positional encoding. So that's standard stuff for transformers, except that for a small detail, they're actually adding this positional encodings in every single layer of the encoder and of the decoder. But that's a minor detail. Again. If you're not familiar how transformers work, please check out my video on transformer. I'll link it somewhere here. But like in a nutshell, I'll try to explain it quickly here. Basically, every of these tokens will be mapped to a query, key, and value. And what you'll do, so you'll have queries. So let me denote queries with this like an arrow. So that's a vector, and query will be in a red. So we'll have like queries, and then we'll have. Let's focus on a specific query. So on this one. And basically, this query will be we'll do a dot product. So that's a way to find the similarity between that query and all of the keys. So we'll have keys for every single like token. And as you can see here, this red arrow and this blue arrow are super similar. They're pointing in the same direction. So that means the score will be really high between these two. So basically, the score between these two, between this blue key and this red query, will be really high. So that means that the value vector, and I'll denote value vectors with green. That means that this value vector will have a high coefficient when we sum up all of the value vectors. So the basic idea is every token attends every other token. So we have this global attention, and we'll just basically figure out these scores by doing query and key dot product, and we'll use the scores to kind of do a weighted average of these value vectors, and that's how we form a novel representation. So that's a super high level overview. That's how it works. You can think of it as information routing, and you do a bunch of those. You just propagate that through the encoder, you get these representations. And now the second part is interesting. So they have these object queries, and they're basically learned. So these are just randomized vectors initially, and you can think of it as this one is maybe, so this vector here, this red one, is looking for a particular thing in an image. So it's going to attend all of this information, and it's going to focus on a particular things. So they have a nice visualization a bit later in the paper. Let me just find it for a second. As you can see here, basically one of these. So they have, as I said, they have 100 output proposals. Here they just depicted 20 of those, and they just, so each of these dots is just the center of the box that proposal it's outputting across the validation set. So that's maybe a mouthful, but in a nutshell, what that means is this one particular proposal, so maybe the first one from the output of the decoder, so the leftmost proposal of the decoder is basically attending on all of the small, so the green dots just mean a small bounding box. So it's attending all of the small bounding boxes in the bottom left part of the image. And as you can see, those different output tokens will be attending different parts of the image. So this one, as you can see, is attending to the centermost part of the image, and also it's attending to those small boxes, etc. So basically all of these, let me go back here. So all of these will be focusing on particular like semantics of the image, let's call it that way. The only difference compared to the original transformer is that here we'll actually be outputting this in parallel. We won't be doing this autoregressively. So we're just gonna output all of the outputs at once in parallel. And the final step is, once we have these output tokens, we just pass them through these fully like feed-forward networks, and we output the class and box information. So that's the, as I already mentioned, this is 4-tuple. This is the just the C++ number of classes, and that's it in a nutshell. So that's how the pipeline is structured. Now I'm gonna go and explain the most important part, and that's how do we match the proposals, and how do we actually do how the loss looks like. So let's focus on that now. Okay, so this is the main part. Basically the whole idea is to find a permutation. Let me go here. So again, I just copy pasted the diagram from the above, and so the whole idea will be the following. So you have your ground truth. So in this case, in the case of this image, we have one red box, as you can see here. We have one yellow box, and all of the other boxes will just be no object proposals. Okay, and so the idea is to find a permutation of this output here so that the loss is minimized. And that means we want to push this red one should be in the first place, this yellow one should be in the second place, and all of the other ones should be here. So that's the permutation that will minimize the loss. And as you can see here, so let's focus on this. So yi is just a tuple of the class information and the box information. And this is just the sigma of I, is just the current permutation, okay? So we want to minimize this match loss between those two. So n just stands for the number of proposals. As I said, they are using 100 of these, and that's hard-coded. So basically none of the images in the dataset will ever have more than 100 objects. So they just took a upper threshold and set it to 100. So we sum up all of the match losses over all of the proposals, and we find the permutation that minimizes this matching loss, and that will be the permutation that we end up using, okay? So that may be abstract still, so I'll try and break it down. Here is the main, this is how the matching loss looks like, broken down into two components. We have this left term with the class probability, and we have the right term with this box loss. And let me try and break this down. So first things first is, if we focus on this proposal, okay, so this is one of the outputs. As I said, it's gonna have the 4-tuple that kind of tells you where the box is, and it's gonna have this distribution over classes, and because it's red, it's probably going to have like this red component being the strongest one, maybe 0.6. And in the current permutation, just treat this as the current permutation of the algorithm. So we'll be comparing red with the yellow one. And because the yellow class has a probability of 0.2, that means here we'll have minus 0.2, And that's not good enough because we want to minimize this. As you remember, so this matching loss needs to go down. So we need to minimize it as much as possible. And the minimal value would be if we had 1 for the yellow class. So instead of having 2 here, we'd have 1. So again, let me just dig into this loss and kind of break it down. 1 just means an index function. So that means that when the ground truth, that's this CI class, is different from the no object class. So that means when we have some class. So here we have this, let's call it red class. Here we have yellow class. So in this case, for the I equals 1, we see here the indices. So indices go from 1 to 6. So C of 1 is red. So that means that because it's different from the no object, we'll have 1 here. So this index function will be 1. Okay, so C of 2 is yellow. So that means it's still different from no object. So that means we're going to have 1 here. So it's -1 times this. And now for the fun part, the probability of the yellow class for the second index here, as we can see, is 0.2. And that means we'll end up with minus 0.2 here. That's minus 0.2, and this is going to give us some value, whatever that may be. Let's just denote it as x. As you can see, the goal will be to find a permutation that minimizes all of these. So if you imagine a permutation where this red is here and the yellow is the second one, in that case, we'd have much lower matching loss. So for that permutation, because this is the red class, we can see it has 0.6. We'll have minus 0.6 here, and that means we are going to minimize this loss even more. So in a nutshell, that's the way how this Hungarian algorithm works. Like, it just iterates through different permutations. It just calculates these expressions and finds the permutation that has the minimal matching loss. And it turns out that corresponds to having red as the first proposal, then the yellow one, and then all of the 4 ones. It doesn't matter the order, because basically, as you can see here, this index function will just be 0 because those proposals have ground truth to no object. So all of these have ground truth of no object class. Okay. Hopefully that was clear. Now let's break down the box loss. And here it is. Here is how it's defined. It's defined as a weighted average of this IOU loss and of L1 loss. As you can see, BI, as I mentioned, that's the 4 tuple. So that's the center coordinates plus the height and width of the box. And what we do is we just take so this is the ground truth proposal. This is the current permutation proposal. And we just find the IOU. As I said, IOU is this thing. The second term just has this L1 between these bounding box vectors. So there's one thing that's kind of confusing me here, because this goes with a plus sign. Let me just see here. So this goes with a plus sign, the box loss. That means we want to minimize it. And that means that obviously when the bounding box vectors co-align, when they're the same, this will go down to 0. That's cool. But the more they intersect, so that means it's a better aligned, this thing is going up. So I suspect that we need a minus sign here or something to kind of for this to make sense. Or basically maybe a specific choice of these hyperparameters can help it work out. But like, no, I'm kind of confused by this part. I think there should be a minus here, or I'm misinterpreting this a bit. Okay. Basically, that's it. That's the L box. And as I said, after we find the correct matching, after we find the correct permutation, we do the following thing, and this is the loss component. This is how the DETR model is trained. We basically go over all of the n proposals. So that's, as I said, 100 in their case. And what they do is they just find whatever the ground truth class is, we find what's the current probability of that class, and we obviously want to push that towards 1, and that's when log becomes 0, so this is minimized. And the second part is whenever we have a class that's not a no object, so basically a class that has something meaningful inside, we'll want to include that box loss, and that's the same box loss as the one as I just explained for the matching procedure. So that's it. That's how everything works. Again, I'm a bit confused by the L box loss, and let me just kind of step out and try and explain this once more on a high level. So again, we are looking for a permutation. So for this sigma, that minimizes a sum over all of these 100 proposals of this L match, so of this matching loss. And that will lead us to find the correct, like, to sort the output so that we have perfect matching with the ground truth. Once we have the alignment between the output and the ground truth, we just apply this simple loss here. So we both want to penalize for the classes not being as confident enough, and we want to also penalize if the if the boxes are too different. So we want to make sure that both the class is correct as well as the bounding box. That's all the information you need to know about how the model works. Now let's focus on the results. There is one more detail though here, and that's we add prediction feed for networks and Hungarian loss after each decoder layer. So that's just a minor detail, but it will be kind of important later on. So that means that we're not only doing these FFNs at the output, at the final layer of the decoder, we're also doing it here and here and here. And although it's conceptually not that necessary to do this, they figured out that it improves the performance, and so they included it, and they'll have later some ablations on this, so that's why I wanted to mention this. So again, we'll have the same procedure I just mentioned, so the matching plus the loss, the Hungarian loss across all of the layers of the output of the decoder. Okay, that's it. Now let's see for the experiments. They compare with this faster RCNN object detection baseline, and they show some really nice results. So again, these architectures are super handcrafted. There was many years of iterations to improve these, and they managed to, using this end-to-end learning pipeline using transformers, they managed to outperform the faster RCNN baseline. As you can see here, focusing on all of the, so first thing I really like here is they kind of mention the flops, the FPS, and the number of parameters, because only when you kind of even those out, then you can kind of claim that you have better performance or whatever, or on pair. And in this case, as you can see on this APL, so that's just the precision for the large objects, we can see that the DETR outperforms faster RCNN by quite a lot, as well as on the medium-sized objects. But here on the smaller-sized objects, it's kind of underperforms. But all in all, looking at this AP metric, we are like the DETR model is better than the faster RCNN. And they did mention it somewhere here in the paper. Let me find it. Okay, so here. So DETR demonstrates significantly better performance on large objects, a result likely enabled by the non-local computations of the transformer. It obtains, however, lower performances on small objects. So the main idea here is because certain objects span like a huge portion of the image, and the transformer having its global attention on all of the layers has the advantage compared to CNNs, which need to go into you need to have a couple of layers before you have the receptive field that can kind of perceive that huge object in the scene, in the image. And so that's the reason why they hypothesize the transformer is performing better for the large objects, whereas it has some problems with the smaller objects. And I can suppose that the reason being is the spatial reduction we have in a CNN. So if we were to not reduce the spatial extent, but then we'd kind of have to increase the computation and the memory footprint, probably like this can be further improved with some of the novel, like efficient transformer architectures. Yeah, I guess that's left for the future work. Okay, let me get back to the results. We saw the comparison with a faster RCNN. Now let's see some ablations. So they showed that, and this is pretty straightforward. I mean, they show that the encoder part of the transformer is necessary. So the more layers you add, the better it performs. But the biggest gap goes from not using encoder to using it. You can see that the AP increases significantly, as well as obviously the number of parameters, as well as the computation and FPS. But we have a huge improvement here, and then we kind of start saturating, adding more and more layers. They ended up using 6, I think, in their encoder, and that's pretty much it. Okay, so let's continue here. Here's a nice visualization of the output of the encoder. So what they do is they take a query token from the output of the encoder, and they then attend, using that query vector, they just attend all of the keys, all of the key vectors of this image. And by doing that, they as you can see here, this query attends to this cow here. So it does some sort of an instance segmentation, as you can see here. So focusing on this query vector here, So this one, basically it attends, as you can see, the small cow. So that's again instant segmentation, similarly for all of the other query tokens. Continuing and seeing other results, this one is super interesting. Basically what they do is they form this synthetic image where they have 6 times 4, so 24 giraffes. And they mentioned that in the training set, they don't have more than 13 giraffes in a single image. And despite that, this DETR model, as you can see, pretty successfully manages to detect all of the 24 giraffes with a high confidence scores. You can see 100, 100. Most of them are above 90%, as I can see here. So that's a nice out of distribution generalization. And that's cool. For this second chart here, what they do is, I mentioned that on every layer of the decoder, they have this Hungarian loss being applied. And what they show is that when they are using one of the intermediate layers instead of the final layer as the output, they get, you can see this progression. So obviously taking the first layer, taking the output from the first layer is much worse than if we take it from the 6th layer. So that's the final layer. And additionally, what they show here, so I'm just focusing on this AP metric, ignoring this AP50 metric. What they additionally show is that this non-max suppression heuristic, which I mentioned in the beginning of the video, basically helps if we are taking the outputs from the initial couple of layers, but then later on it does not help, and that's by design, because the Hungarian loss and the matching was meant to make this the proposals unique, and so we don't have to kind of filter out similar proposals because that's handled by the loss implicitly. Okay. That's that part. Here they have interesting visualization of this time decoder attention mechanisms. So we take one of the proposals, one of the tokens from the output of the decoder, we use that and we attend to the outputs of the encoder network, and that's what we got. And basically, as you can see, focusing on one of those output tokens, so whatever, like whatever the index of the orange token is, you can see that it attends to this to the extremities of the elephant. This kind of explains why the encoder is necessary. So encoder kind of does this this initial segmentation of the instance, and then what the decoder does, it learns how to kind of do contours of the object, which is necessary for it to find the convex hull or the bounding box in this case. Of that object. They just kind of work in symbiosis and help each other. And again, for the blue token, you can see that it again attends the extremities, and that's how it figures out. So these components here are really important for the detector to figure out that this is an elephant. And similarly in this image for zebras, you can see a green token attending here to this zebra, the blue one to this zebra, and the orange one to this zebra. Okay, that's it. They did a couple more ablations. I mentioned that the spatial, these positional encodings, they have, it's pretty intricate. I can kind of go to appendix and show you this part. So as you can see here, the spatial encoding is added to the keys, to values in every single layer, and it's also added to the keys of the decoder as well. And you can see these object queries, which are also positional encodings, but they are learned, not fixed in this particular case. It's again added here and there, so it's pretty convoluted. But like you can also do it the same way as the original transformer, which was only at the input. But they showed that this increased the performance in the ablation table I was just showing you. So let me get back here. So yeah, basically here they showed that adding these positional encodings on every layer at the attention module just increases the AP metric compared to all of the other combinations. So I don't think we can extract something super intuitive here. It's just that this experimentation showed that it's just better to kind of include them in all of the layers. Okay, they also try and do ablation of the L box component, which I showed you, and they try using only L1 or try using only IOU, and it turns out that if you ignore the IOU, you have a significant decrease in this AP metric. So you have to include the IOU. L1 is just extra, and using both of those obviously just increases across, just boosts up all of the metrics. Okay, that's it. Yeah, I already mentioned this one as I said. So this just shows how different output those they call those prediction slots. I just call them tokens of the decoder. Basically, you can see that each of them attends different regions of the image and different types of objects of boxes. So you can notice a trend that this red dots are equally present across all of these 20 prediction slots out of the 100 they have. And the reason being, those are, I think, huge. They say somewhere here, huge horizontal boxes or something. So red to large horizontal boxes. And it seems that the MS COCO dataset just has a bunch of those objects which span the whole image horizontally. So that's why all of these prediction slots or tokens learn how to kind of focus and attend to those. Okay, that's pretty much it. Let me see. I'm going to briefly just tell you about this. They also showed that just by simply modifying the DETR pipeline, by adding this additional like segmentation head, they can also do really well on this panoptic segmentation task. And the idea is they just do regular object detection training of the DETR pipeline, so that remains the same, and then they just append the head and they freeze the DETR and they just train the head itself, and they show some nice results. You can see here. Like segmentation of this giraffe image and bus, etc. Yeah, they just show that this works really well here in this table, comparing it to other baselines like this panoptic FPN, etc. And they just report nice results there as well. So that's pretty much it. It's exciting. So the main two components again are using transformers and learning end-to-end using this match plus Hungarian loss logic. And that's it. If you like this video, share it out, subscribe to this channel, and until next time, bye bye.